seminar, and both PNNL and an IAEA collaborate on a number of initiatives, and we do this in order to expand the value and impact of our parallel networks. And this seminar today is one such joint offering. Before I turn things over to Horst, I want to thank our PNNL colleagues, Kelly McIntosh and Melissa Perdue. They've helped us organize and run today's seminar. And for your information, you've probably heard it, the seminar is being recorded. The recording of this seminar will be made available on the RemPlex and Environet web platforms, as well as copies of the slides that you'll see today. Horst, would you like to make any opening remarks?
Yeah, thank you, Karen. Thank you very much. Welcome to everybody and to our panelists. Before we start our presentations, I want to take a moment to promote the RemPlex Global Summit on Environmental Remediation. This will be a hybrid in-person and virtual event held at a PNNL in November 13 to 17, 2023. RemPlex Global Summits provide a forum for examining the challenges and barriers, innovative solutions for successful remediation and long-term stewardship of contaminated sites. All these things are very important in the scope of what we all do. This year, we will have 3 case studies, 9 oral technical sessions, a poster session, and a historic Hanford site tour and training workshops. We hope you will join us, and our deadline for abstract is being extended. And yeah, and I also want to call your attention to the International Conference on the Safety of Radioactive Waste Management, Decommissioning, Environmental Protection, and Remediation, Ensuring Safety and Enabling Sustainability. This is an IAEA conference that will take place from 6th to 10th of November 2023, Vienna, in Austria. The conference takes place just 1 week before the RemPlex Global Summit and can be followed virtually through the IAEA conference meetings app. So I really invite you to pay attention and, if possible, attend to both events. One done in cooperation with PNNL, the RemPlex, and the other one being a international conference organized by the IAEA. With that said, I turn back to you, Karen.
Okay, thank you very much, Horst. So we are now going to move into the individual presentations, and let me bring up a slide to introduce our speakers again. So, all right, there we go. So our first speaker is Bruce Marvin, and he'll talk for about 25-30 minutes and then be followed by our second speaker, Norbert Molitor. Bruce is a senior principal environmental engineer with Geosyntec, and I apologize, Bruce, I see that I incorrectly have you associated with PNNL on the slide. We'll get that fixed. Bruce is in fact with Geosyntec Consultants. He's based in California and has more than 30 years of consulting experience. He's focused on civil engineering, soil and groundwater remediation, and facility closure. He specializes in project strategy development, technology selection, engineering process design, and quality assurance procedures, and he's worked with commercial and governmental entities around the world. The title of your talk, Bruce, today, if you want to bring up your slides, is a Survey of Soil Remediation Technologies.
Thank you, Karen, and good morning, everyone. It's an honor to be affiliated with Pacific Northwest National Laboratory. I do work for Geosyntec Consultants. I've worked a bit at the Berkeley National Laboratory, but I've worked with our colleagues at PNNL for a couple of decades now with the commercialization and development of remedial technologies, specifically more in the chemicals and metals space. And what you can see on the screen today is the organization of our webinar. So really our goal is to communicate to the audience and our IAEA partners, as well as our PNNL partners, opportunities for innovation that we've experienced in the last 10 or 20 years, with a particular focus on what's new and later, but I will go back in time a little bit because I can't help myself. And I'll be presenting the beginning of the framework that you see at bullet number 2 to introduce what Dr. Moliere and I have discussed as far as a framework for complex site remediation and strategy decisions. Really what I like to think about during this talk is this is almost like what we do under the Superfund process or the CIRCLA process, where we do a feasibility study. And what we'll be thinking about today are big picture technologies, how they fit into control or elimination processes. And then are there subsectors of those technology categories that are ripe for either future innovation or recent innovation. So that's what we hope to communicate to you. And when we get down to the middle of this framework for soil remediation planning, I will turn the speaking role over to our colleague, and we can entertain one or two questions depending on how we do on time. I'll do my best to keep us on time today. And that's how we advance the slide. So this is our framework. And Norbert came up with this framework, and I thought it was very interesting. It uses slightly different technology than what I'm accustomed to in the organics and metals space. But really what I've found in my practice working with radionuclides and metals as mixed waste is that the concepts are quite identical, but it's kind of like speaking Spanish versus Portuguese, a slightly different dialect of the same process and thought that goes into. And what I'll try to do throughout my overview of some of the more recent innovative processes is kind of put them in this framework of, is it an elimination or a treatment process, or is it a control process, more like a containment process? And so when we look at radiological constituents, oftentimes the half-lives are extremely large, and to get to 8 half-lives of control to mitigate the exposure, we actually have quite a bit of time. So in my parlay in the organics and metals world, that's almost like moving the waste to a disposal facility like a landfill, versus the elimination or the destruction side are processes that destroy the contaminants. We can do that with organics like heavy fuels. Can't necessarily do that with a radionuclide, which we might be able to transform, but we may not actually be able to permanently dispose of or destroy until we just allow time to pass. So that's the context with which we'll talk about. And some of the technologies that I'll cover a little bit later are a combination of both elimination and control, but I'll try to point that out as we go. So to start off, I'll have a couple of slides just to talk about the context of the problem, kind of what I like to call the complex site problem or the emerging contaminant problem. And really, you know, when we put this all into frame of reference, first we have to understand our regulatory context. And I listed on the screen a few different regulatory programs that we work with, particularly here in the United States, where I do most of my practice, although I've worked overseas under different state or provincial programs. But it's really critical that we understand the regulatory construct that we're working in and work to make a relationship with our presenters and our regulators to get them to believe that this innovation process or these technologies where we will find innovation opportunities are valuable to the overall progress of moving a particular project or site through the regulatory process so that we can control exposures and achieve ultimate net benefit. In our chemical engineering space, in our chemical contaminant space, over the last 30 years of my career, what I've seen is every decade or so, numerical cleanup standards go down. So in a way, we can think of it as the chemical space is emerging and moving towards more like the radiological space. And the radiological space, we've had a lot of benefits of being able to detect very low levels of contamination. And these emerging contaminants, we're starting to see that in the last 10 or 15 years in the chemical space as well. And so what the point of this slide really is over on the right-hand side, you can see a table that I produced in 2007, 2008, that talked about a bunch of new contaminants, 1,2,3-trichloropropane, N-nitrososodium methylamine. And you can see these regulation levels, the response levels, the notification levels. Those are California-based drinking water standards. And those are requirements when a water purveyor or someone who sells water to a distribution system has to notify the consumers of the presence of these chemicals. And the point of this table on the right is to show that we're moving into much sub-microgram per liter space, even in 2008 and 2009. And what that causes is challenges for in situ processes, and particularly in situ destructive processes, where if you look over on the left, you can see that we get down into the middle and we start experiencing problems of competition kinetics. So we might have a very small amount of one of these emerging contaminants in a solution with many, many, many other solutes. And so the competition for reactive species from other constituents of water becomes more and more important as we chase lower and lower cleanup goals, essentially. As well as what we've learned is that we've seen separation of different plumes. So we discharge one of these emerging contaminants to the ground. It begins to move through the ground, kind of like a coffee filter and a leachate problem from a landfill. And we've actually seen physical separation of plumes where we might have a more soluble constituent that doesn't absorb the soil as much, move away and ahead of a contaminant plume that's left behind. So what I would like to convey to the audience is just we need to think about broadly these new emerging contaminants. And at the bottom left is the most recent class of contaminants, the per and polyfluorinated alkyl substances, PFAS. And PFOS, the sulfonate version of this long hydrocarbon chain with lots of fluorine all around it, makes up our Teflon, it makes up our Gore-Tex, it makes up our Scotchgard, our trade names, and creates water repellency that allows these materials to have fabulous properties in the marketplace. But what we're discovering is extraordinarily low toxicity levels. And so you can see when you contrast to the right the table from 2008 to the bottom left corner of the slide to the concentration levels in there, we've gone down multiple orders of magnitude. And we found that these PFAS compounds are present in the atmosphere and the globe ubiquitously. And so we find these compounds now in polar ice, largely because we have improved analytical detection limits. And we will face challenges as cleanup professionals and in remediation engineers in the future to deal with that fundamental nature that there's a very small quantity of these materials that we're trying to transform. So as we move into our process of thinking, we understand our regulatory environment that we're working in. We begin to be cognizant of the different types of contaminants we may deal with. And historically, we might have seen asbestos as a problem or polychlorinated biphenyls. And now we're finding these more and more esoteric compounds that require more specialized expertise to identify, understand the movement, fate, and transport of these compounds. And one of the techniques we like to use in the chemical space is the development of what we call conceptual site models. And I've shown two here from two projects I'm working on right now. The one on the right is a conceptual site model for mercury vapor intrusion. The one on the left is a risk-based conceptual model for mercury in shallow soil. So in these conditions, we're looking at mercury at 20 parts per million, milligrams per kilogram, being a hazardous waste threshold. And then we're looking at mercury in indoor air at 0.13 micrograms per meter cubed. So at that point, we're at part per trillion levels instead of part per million levels. So these conceptual site models help guide us on what is the most important mechanism of exposure for the person, which is on the left, the exposure conceptual site model, where originally 10, 15 years ago, we only really thought about leaching to groundwater and said, well, if that material gets down in the groundwater and out into the water supply, we're then going to have exposure through ingestion or inhalation in a shower. And now we fast forward 20 years and we're looking at the soil vapor to indoor air pathway is about dominant in 75, 85% of the projects I work on now. So now we're looking at trace amounts of these chemicals that load up into the soil vapor. And when things like weather conditions, flooding, what you can see on the right is we identified that pooled water in this street because of a failed storm drain actually causes the physical process of pushing the soil vapor that's loaded up with mercury during the summer into the building envelope, creating exposure potential for people. So that helps guide our remedy selections, is how are people being exposed? How do the contaminants move through the environment and make it to a receptor, which helps guide us on decisions like how innovative do we need to be with these technologies? How low can we go? So with that, I'm going to move in a little bit more into the more of a just direct discussion of what are 9 examples of chemical remediation processes that have seen recent innovation in the workspace. So I'm just checking my time. Bear with me while I get organized with my timer. So in the control technologies in the top left, you can see that typically control often means removal and offsite disposal. So we can control on site. Norbert's going to talk about some European systems for containment of radiological waste later in his portion of the talk, which might be more localized offsite disposal. But in what I look at in my practice a lot is, do we dig this material up, haul it to a new landfill, and what are the social and environmental costs of doing that? And that's where a lot of concerns about sustainability, which is the use of fuel and the emissions of CO2, to be a balancing point in the criteria that we use to evaluate and select technologies, which was put forth in the circular regulations long ago. But we've seen that in the last few years, we're adding in a sustainability element to it. And so the elimination technologies, the in situ and ex situ processes shown on the screen, really help us put an end state to that contaminant by mineralizing it either to carbon dioxide and water. The carbon dioxide may turn into bicarbonate, or we can transform a species like a metal from a mobile species to a less mobile species. So that's what I'm trying to show you a little bit more of. This is a first project that I'm going to present to you. This is a Berkeley National Lab mixed waste deactivation and decontamination project. So when you're watching the movie Oppenheimer in the next few weeks, keep an eye out for Berkeley. This is the original Old Town area of Berkeley when it was the Berkeley Radiation Lab. In the top right corner, you can see where we started in 2009. The blue stars indicate buildings that we selectively characterized, disassembled, remediated, packaged, and hauled off site. And then you can see in the middle in 2020, there's a number of buildings gone. And in the bottom right corner in 2023, we finished that program and basically rendered that piece of the Berkeley National Lab ready for reuse to be part of the expanded advanced light source and put aside that pre-Manhattan project legacy. So really the interesting thing about this process for me was this was one of the first large radiological projects I got involved in. And the first bullet on the top left was something that we had to talk a lot about as a project team while we're developing our innovative methods. And that is that we saw radiological waste throughout this whole area. The whole area is classified as low-level waste. But we found a diversity and a patchwork of chemical contaminant hazards. Free mercury rolling out from under a retaining wall, asbestos building materials, PCB underneath caulk, beryllium in sewers, more mercury in sewers, because it was pretty common back in the day to pour your mercury just down the sink and off it went. So, you know, really on these kind of dig and haul projects or excavation and offsite disposal projects, really the opportunities for innovation really focus on project planning, workflows, and how we collect data, the data collections, and how much data we do collect. And Norbert will tell us a little bit more about project planning and workflows optimization on a Chernobyl project that he'll talk about in about 15 minutes, maybe 10 minutes. So moving to the next level, we have a more classical technology, soil ventilation. It's a class of technologies. And I bring this up today because we still use this technology quite extensively for abatement of the subsurface soil vapor to indoor air pathway. I like to call soil ventilation a larger category of technologies. So what you're seeing in the bottom right is called soil vapor extraction. So that's a higher volume process that's intended to volatilize contaminants and either collect it on a fixed bed absorber like activated carbon shown in the picture on the right, or you might have a catalytic oxidizer that burns that material as it comes out of the ground. But ultimately, the material is concentrated and destroyed. And really what controls the effectiveness of this technology is the volatility of the contaminant, how quickly it vaporizes, and how far you have to move it. So as ironic as it sounds, we innovate in this space on both the operations and maintenance, and potentially there's even a whole category of vendors out there that will add large amounts of heat. They will boil the subsurface, they will heat beyond the boiling point. But I don't find that very innovative because heat is very predictable. How you can move through space, how it can move through time. The hardware is very proprietary, but the process in and of itself is not that much. But really, the other thing that's escaped that I found interesting over the years of looking at soil ventilation projects is that people don't innovate very much on the distance of travel that's necessary. So ultimately, in my opinion, and our experience at Geosyntec, more wells, closer spacing means faster timeline and higher effectiveness. And really, the cost of an individual soil vapor extraction well is extraordinarily low. So if you double the number of wells, you're going to spend far less money than if you start pumping in kilowatts of heat into the ground on a very large well spacing. And PNNL has a really neat tool called the Soil Vapor Extraction End State tool. You can see a copy of that in the top right corner. It's a spreadsheet model. And what we've really found that interesting in an innovative space is it's innovative in its ability to bring the regulator into the decision-making process to agree that the end state has been achieved. So that consensus building process applies to innovation across all of these categories in that regulatory context where we really need the regulator to agree and to understand the data we're collecting, understand the conclusions that we're drawing. And this PNNL soil vapor extraction end state tool really helps with that. Whereas at the bottom of the slide on the left, you see subslab ventilation and subslab depressurization. Those are two other versions of soil ventilation that I'm not going to spend a lot of time talking about today, but they're really containment technologies and they have different benefits. And we really moved a lot towards subslab ventilation, more in our practice at Geosyntec than subslab depressurization, which is kind of a subset of ventilation. Now moving next, this is a really neat new technology. It's a thermal technology. This is a patented technology that uses the contaminant as fuel. And what you see here is smoldering combustion. So again, there are a few other ways you can do a heated soil ventilation process. You can do conductive heating using essentially electric stove elements. You can do resistive heating, an array of electrodes, and use the ground as a resistor, and it creates the heating. And this process is kind of interesting because it uses the contaminant, a heavy fuel, as heating. And it can be used in situ or ex situ. So smoldering combustion is like your charcoal briquette. So it's your solid phase combustion. You can see the glowing red on the screen. That's the actual combustion itself on the surface of the charcoal briquette. And so what you need is the combustion triangle to make all of this happen. The heat is provided by the contaminant. The oxidant's provided by air. So we just blow air through the ground, and the fuel is the contaminant itself. However, it's important when thinking about this smoldering technology that you have to be able to move air. So if you can't get air to where the contaminant is, you can't have smoldering combustion. So in a way, it also is a self-regulating process because when you run out of oxygen, it shuts down, which was something that when I first heard of this technology that my colleagues developed about 15 years ago with the University of Dublin, I believe, one of the Irish universities. It's been really quite interesting to see how that comes to pass. So again, you can see the contaminated fuel or waste, in this case, heavy hydrocarbons, manufactured gas plant tars, the air that's injected, and that's usually atmospheric air. We have kicked around using oxygen before, but that scares people even more. And then the heater element itself, so you heat up the ground to about 700 degrees C, and then this auto combustion front begins to propagate, and you add no more external power to the system, and you get combustion. So here's what it looks like at the field. And this is a 37-acre site we did in New Jersey. You can see massive amounts of contaminant, massive amounts of infrastructure, and a lot of safe work reporting. And ultimately, the neat part of this process is the contaminant was the fuel. We burned it out of the ground, and it achieved regulatory site closure in 2019. Now I'm going to talk a little bit more about a slightly different process. So now we're going to talk about how do we do shallow soil amendment. So in the case of STAR, we drill holes, we blow air in. We need a certain amount of pneumatic permeability to make that viable. Shallow soil amendments, on the other hand, are often blended into the ground or mixed into the ground. And there are many, many, many different types of commercial products that can be used. I'll just try to quickly go over this. So in situ stabilization, cement addition has been done for 35, 40 years, thousands of sites. We're now hybridizing that process using Portland cement and sodium persulfate, and that's what I call ISS ISCO in the fourth bullet. And that has permeability reduction and contaminant mass loss. And then the third bullet, we talk about different ways that we can mix this material in. And the key part is the depth of the application. And then ultimately, I'm going to focus on a couple of different amendment types, the Daramed and the Metafix, on the next few slides. So Daramed is a product that was produced by FMC originally. Now they go by Evonik, and it's targeted towards pesticides, solvents. And as you can see, the interesting part is both of these are a mixture of different amendments. So there's an iron oxide component, there's a sulfide component, there's a zero valent metal component. So really, these are multiple mechanism technologies. Here's what the tilling application looks like in the upper left. Down on the right, you might have, bottom left, you might have more of a flooding application. On the top right corner, we have an ex situ cell where we've mixed it in cell, and you can see the plastic liner to keep that solution in there. And then, of course, in the bottom right corner, you see one of the most classic methodologies applying these soil amendments, which is you do an excavation and you chuck it in the hole and you mix it around a little bit with an excavator and you hope for the best. So depending upon how you want to apply these amendments can really have a strong effect on their overall efficacy. Unfortunately, I don't have enough time to go into that today, but for Metafix, I just want to show you how it works. So you can see there's a reductive precipitation process on the left generating a lead sulfide. So the generation of metal sulfides is used widely across practice, from acid mine drainage to these kind of anthropogenic metal sites. In the middle, you've got reduction, so a chemical process to convert the process to a less toxic and less mobile form. And then on the right side, you have adsorption. So essentially, we're adding to the assimilative capacity of the soil by adding a mixture that allows for physical and chemisorption and prevents mobility, but yet retains that material in the soil. So on the right, we have control, and on the left, we have treatment. Metafix is a similar process. Oops, sorry. Is a similar process. You can see there's a couple of different types of Metafix, and I'd be happy to take any email request to redirect folks to the Evonik technical for this process. That's really outstanding for helping you select which of these combined treatment processes do you need. And then ultimately the question is why? It's to avoid landfill disposal, and you want to have beneficial use on site. So when you go through these process and these technologies evaluations, if you have a multiple step process where you have some combination of treatment and control, elimination and control, you can reduce cost by reducing the amount of handling, you can preserve and reuse the soil, and then ultimately you can eliminate hydrocarbon emissions, trucking costs, the safety associated with transporting to a landfill, and you have a greener and more sustainable technology. Getting close to the end here, so I'm going to start moving even quicker. But one of the final two, there's two more technologies I'm going to touch on really quickly. Reactive gas injection. And here is my self-serving slide from 1998. This is the first ozone system of this size used for vadose soil treatment. You can see in the bottom right side, we destroyed PAHs and pentachlorophenol quite effectively. This site has since been closed. And really, with a key element here for looking at these ozone technologies is what's the overall amount of ozone you need to achieve your endpoint. And all too often, there's too much contamination in the ground, and you might have to turn to a smoldering, a thermal, or a soil amendment approach. Here is some innovative work that Geosyntec and PNNL have been doing. Geosyntec's been taking this hydrogen sulfide injection process to the field for hexavalent to trivalent chromium treatment. You can see it works fast, and then it gets scary pretty quick because you put 500 ppm of hydrogen sulfide in the ground and you have a permissible exposure limit of 20. Same thing happens with ozone. We put ozone in the ground at 100 times the IDLH, the immediately dangerous to life and health level. So these processes can be engineered, but there's also a lot of, stakeholder engagement with safety professionals that need to be worked through. And then PNNL has done an incredible job of transforming these in situ reactive gas technologies to radionuclides. So here is a slide describing ammonia gas for the fixation of uranium in the subsurface. And you can see that there's a pH effect, there's a mineral effect, there's an adsorption effect, and there's a precipitation effect. And for the sake of time, I'll keep moving. Same process. This is hydrogen sulfide plus ammonia to deal with technetium-99. So again, injection of both of these gases, one creates a chemical reducing situation, the other changes the pH. And if you understand your conceptual site model, your geology, and you have some really bright geochemists like you do at PNNL, you can fixate these contaminants pretty effectively in the subsurface. Not done very often because it's a little expensive and a little bit scary. And then finally, the last technology I'm going to cover, and then I'll turn it over to my colleague Norbert, is electrokinetics. And we've been working with this process for a long time. Back in the 90s, there was a patented process under the EPA site program called the lasagna process, where you made layers and you rolled it all up. But basically what you have here is what Geosyntec's been working on for the last 10 years. So in the bottom right, you can see permanganate moving through a soil core. The permanganate flows from the bottom up, and an electric field is placed on the system. And what you can see is actually that the direction of flow is really independent. But what that electrochemical process does is it instigates the movement of water through the application of a direct current field with a very low wattage. We can move electron donors like we use for food. We've done this with bioaugmentation. We've moved Dihelicocoides maccarti through a clay into a clay to achieve 90% removal of mass and complete dechlorination where there was none before. And then we have another process we call EK tap, and that's an electrokinetic delivery phase where we push persulfate anions into a formation with DC power, and then we flip to AC and we then heat. And so the tap is thermally activated persulfate, but it's an electrochemical enhanced delivery. So this is a neat technology that came out in the 90s for the movement of charged ions through formations. And now we're using it to deliver remediation amendments quite effectively. So with that, I will just pause and bring it back to a crossover slide. And thank you for your time, and ask Karen to transition us over. Thank you, Karen.
Sure. Thank you very much, Bruce. You covered a lot of interesting stuff. We can take a couple of questions on Bruce's presentation. And right now we don't have, unless one has just come in through the chat, we don't have a lot of questions. Oh, we do. We have a question for you, Bruce, in the chat. So I'll just read it directly for you. Acid drainage is a well-known problem in the mining industry. When drainage occurs in mining areas, there's a problem with leaching of uranium and its decay products. What suggestions for in situ treatment might you have to prevent the acid drainage from occurring?
That's a really excellent question. It's very hard to do in situ treatment for acid mine drainage mitigation. I've seen attempts done with electron donor donation, injection, foam injections. And really what I've seen most effective is the control and collection of the leachate. And we've worked a lot with biochemical reactors where we might have a limestone cascade followed by a pond that would have a woody substrate, a cellulose substrate. And we're trying to use the sulfate from that acid mine drainage to create a reactive sulfate or sulfides, which then fixate those metals in the treatment bed, and they can all flow by gravity. But unfortunately, I don't think, Karen, I have a good solution for how to deal with the bulk problem of, let's say, a mountain, which is been excavated with all kinds of mine works, and we want to prevent the acid mine drainage from forming. But Norbert, of course, has his hand up, and he's a mining engineer. So Norbert.
Excellent. Yes, Norbert. You're on mute, sir.
Now you hear me?
Yes, we
okay,
do.
Acid drainages or acid mine waters are really a problem, also for uranium mines, but also for other mines, metal mines, heavy metal mines. And yes, I agree fully what Bruce has said. So you can work on the leachate. That is, of course, a good action or intervention point. But you have also some in situ methods which are always applicable, although they will not reduce the acid drainage fully. They can reduce it to more than 90%. One is flood the mine, because water has only compared to dry air, very less oxygen in, so the oxygen potential and the acidification potential will reduce rapidly. But before doing the flooding, you can backfill the mine. Normally we like to, at least in Germany, we made good experiences with backfill with fly ash, which is a waste from the electric industry, but which is an excellent backfill to stop the acid reaction. So it means which will reduce considerably. In some exceptional cases, you can even flood a mine such that there is no exchange with the surface water anymore. But it depends on the geology, and it requires a very, very careful flooding process, which takes sometimes 20 years. But you can at least reduce the source term extremely, that the methods which Bruce has set then comes to a level which are manageable also financially. Thank you.
Thank you. Thank you both.
And if I can add, because this is a topic that deserves one specific webinar. One point I want to make is that you need to understand precisely the nature of the acid drainage and the process in charge of that. The treatment of the leachate, there is one issue with that, because it can take very, very long time, and the operational costs related to this treatment can be very high if you integrate it in the long run. So we have already examined some techniques that would prevent the acid drainage to take place, depending on the source. If it is in a waste rock pile, for example, by reducing the diffusion of oxygen, that is one of the driving forces for the reaction. By doing that, you reduce the amount of acidity that is generated. The problem is how to keep this system stable in the long run. So I just want to highlight, to flag the point that treatment of the leachate can be a short-term solution, but in the long run, you might need to treat this for a long time. And another point that I want to make, Norbert, is that you can also think about recovering some species from the acid drainage, like for example uranium. You'll not run a mining from recovering uranium from that, but since uranium is there, and the acid drainage is doing exactly what the process does, you can somehow take some resources from that by recovering uranium, and some places this is exactly what they are doing. But as I said, it deserves a whole webinar, and that might be a very good topic, Karen, for a new one.
Yes.
That we could explore in more detail. Thank you.
That's a good suggestion, Horst. Bruce, I'd like to ask one more question specific to your presentation, and then we will transition over to you, Norbert. I was really interested in the smoldering combustion technology, and can you expand just briefly on factors that lead to choosing the in situ versus the ex situ applications?
Certainly, Karen. A lot of that relates to the actual location of the waste originally. We first started working with the ex situ application when we were presented with a challenge of dealing with a lot of oil exploration, sludges, and essentially the waste product from drilling the oil. And that's what led to that first. So usually if the ground has adequate permeability without being disturbed, we would use the in situ process. And you can essentially do an assessment of the soil at any site to say, would this be a good site where I could inject air and get air to move, say, 4 or 5 meters away from your injection point? At that point, you're able to do the process in situ, and there's no need to exhume the waste and use it in an ex situ application. But there is kind of a limitation that a lot of soils don't have that kind of level of pneumatic permeability. So I think there's the two situations, either when the waste itself has been accumulated above ground already, or the subsurface conditions have too low of a pneumatic permeability. You can't get the air. If you can't get the air to where the hydrocarbon is, you can't smolder it. And hopefully that answers your question, Karen.
Yeah, thank you. Horst, should I turn it back to you?
Yes, of course. Oh, where is my notes? It's kind of thinking about the questions there. So let me turn on my video, please. Wait, bear with me. Okay, now we go for presentation from Norbert. So I have the pleasure to introduce Norbert Molitor. Molitor. He's the managing director of Pleiades GmbH, or GmbH as you wish. He holds a master's degree in mining and a PhD in applied mechanics and process engineering, and over 40 years experience working in the mining and uranium industries. So since 1988, he has worked on a broad cross-section of environmental remediation projects, and that includes the contaminated sites from hydrocarbon and chemical industries, contaminated military air bases, mine closure and legacies, warfare industry legacies, and radioactive legacies. So his talk will be pretty much driving considerations for innovation in environmental remediation. And before I give the floor to Norbert, I just want to make sure that you understand that this webinar involves radioactive and non-radioactive substances. And the reason for that is that in many cases, you have mixed contamination. So you will not be able to think only about radioactive elements, but you also need to think about non-radioactive species. So it's always good to keep an eye on these situations, and this is why we decided to combine these two topics in just one webinar. With that said, Norbert, please, the floor is yours.
Thank you for the introduction. I will try to share my presentation. Do you see my presentation?
Yes, sir.
Yes, yes.
That's good. So I will drive very rapidly through some of messages I want to give based on my experiences over the last decades. I will look on the drivers in remediation, especially for soil remediation for legacy sites or legacy situations, and the challenges which are specific for them. And then based on that, not to become too theoretical, I just want to show on a few examples how innovation has taken place and how it really provides a benefit. My focus will be on the remediation of legacy sites, but always or predominantly with radioactive contamination, but the thoughts are the same as for totally non-radioactive contaminations. The problem of legacy sites is that the original design, the operational and post-operational history of the sites are often unclear. So this also relates to the inventory, which is often uncertain. It means type, distribution, and the condition can not very well described, and we don't find records. And the third main driving point of these legacy sites is that the today conditions does not fit to the normative and regulatory requirements as we would like to have them now, but due to the history, these sites exist and we have to do something. And this means that the remediation strategy typically implies, first of all, we have to address all these unknown related to the history and the inventory, and we have to address the risks arising from that inventory. And based on that, it means the inventory and the risks as far as we can understand them. We have also to analyze the consequential risks related to, or linked to any corrective or action or implemented or not implemented. Sometimes you prefer not to touch it, which always comes to a so-called justified site and situation specific approach. So there is no blueprint for everything, but there are some principal elements. So if you go, the justification that you are starting to think or to take action is that you have a contaminated site, and due to that knowledge, you perceive or you know about the danger of the contamination. Danger means that you have either the need to protect people, to protect the environment, to protect properties of third parties, and you want to take justified measures, means taking responsibility. And normally there is always a set of standard actions, which is coming from investigation, assessment, implementation of corrective actions, and of course always the proof of results. In reality or in practice, this means you have either to find a way to eliminate or control the contamination. This is the slide which Bruce has already shown, and I think this is really the main point. Either you eliminate or control the source, or the source means the primary source, so where the contamination comes from, or the secondary source, which can be a plume. Also, this has been already addressed by the presentation of Bruce. The objective of all of these, regardless what you are doing, is always to find a safe, effective, and efficient solution that you can proceed. And this is the justified measures. You should be aware that there is, on one hand, the technical processes, which I have already raised, so the investigation, assessment, implementation, and proof of results. But there are also a lot of management processes. You have to understand what the problem is. So a system analysis, you have to always think about the feasibility and option studies. There will be a decision process behind it, licensing and funding, and you have to implement it. And often it is overlooked that it is not purely a technical problem. It is often also a schedule and a financial or economic problem. You have to always respect the boundaries, which are, of course, physical. It means geography, climate, etc. But there's also others like legal, administrative, or contractual boundaries, which may be linked to a site. It's about ownership or whatever commitment which are linked to that site. You have another boundary condition, which are the available resources, which are technical resources. So are there specific technology available? The financial resources and the know-how, of course, also. And last not least, at least in our countries in Europe, we are often looking on the so-called other, often underestimated boundary conditions, which is the public, the politics, and the partners. And if you say partners, you can, of course, also say the enemies of what you want to do. You have, fortunately, a good toolbox, many elements. I don't go in detail for all of that. But I think there are two things which I want to highlight. On one hand, it's really a risk register analysis and mitigation plan, and the graded or staged approach, as also is recognized in the nuclear world, but also in the non-nuclear world. This will mean that you will have a lot of programmatic and configuration decisions until you will come to it. Just a last slide on which is a little bit theory. If you want to achieve safety, effectiveness, and efficiency, this is the triangle on the left side. It is a trilateral conflict, so you cannot satisfy all parties at 100%, but you can always find a compromise, which needs to be always aligned according to the real needs, the strategy, and the technology. And who are really representing these say key issues. These are the key stakeholders, typically the implementer. It can be the operator or the owner of the site. It can be also someone else, can be also state organization mandated for that. You will have a sponsor and you will have an authority, and you need common understanding on the real requirements. Bruce has spoken about the legal framework. Then, of course, the technical framework and the approach. The left-hand side, I always like to put that in the category of performance indicator, and the right side on the key stakeholders. So it will come to performance management and stakeholder management. Interestingly, the efforts you have to invest or you have to apply, so it means on the costs, if you're thinking in dollars or euros or whatever other currency, these are triggered by the needs and the waste, the time and the risks. And the waste, time, and risk are typically triggered by the requirements, logical framework, and the approach. I'll come to some examples to that, and also on innovative approaches, how they came. For radioactively contaminated soil, typically bulk, very low level or low level waste, you have not so many different options. As Bruce has said already, radioactivity, it's difficult to destroy except by the natural decay. Of course, there are some very specialized technologies, but which are out of economic feasibility. So you will have the confinement. The in situ confinement has a very low acceptance, but it can work sometimes. The ex situ confinement has a high acceptance. Typically, you will bring it to a licensed disposal. Can be different types of disposal. You can, of course, go for decay storage or natural decay, but the decay storage we have observed that's specifically for short-lived radionuclides as applicable. Normally, you always do a selective excavation, which you can categorize as an in situ sorting, which is really standard. And you can make a sorting after excavation, which is a typical batch-wise classification. And this is also very standard. The question is there potential for optimization of these standard options? So typically you have a combination of 2, 8, and 9. Could be a good, that is the reason I have put them in bold. Coming from the commissioning of major nuclear facilities, there has been really cases, and I'm coming to a case where we had a primary waste of about 40,000 tons of low level and very low level waste, but the problem was it contains long-lived radionuclides, so which are unfortunately not subject for natural decay in reasonable times. The idea was really the task from the operator. He wanted really to clear the site as soon as possible. So he needed an effective diversion of all the materials on his site. And the first attempt was to bring it all to a low-level waste disposal, which was quite a very high cost. So he was looking for ways to minimize the radioactive waste volumes. And in difference to the classical standard, it was decided to go for the continuous classification, characterization, and classification in a moving bed. So not in a defined geometry, but in a moving geometry on a conveyor, which is not standard at all, also not for the regulator. And to check whether this could go, this would fly. And the main motivation was also really the time, because that was the only way to go for the time. It is the case is in Belgium. It is a former fuel fabrication plant. And at the end, it could be even much more than initially expected. 36,000 tons of the almost 40,000 tons could be unconditionally released, and 2,000 tons could be conditionally released. It means sent to a landfill, and only 1.3 tons required sending to a radioactive waste disposal. So the benefits were very obvious. Time reduction is for sure was the initial main motivator, but also the waste reduction, but also exposure reduction and low technological risks. Because if you go the slides on the right hand, you see the whole equipment. The main key issue is inside this hole. Here is the where you will bring the bulk wastes. Then it will be homogenized, and big pieces are like trees are sorted out, and then comes to a sorting facility. There's a line for the radioactive waste, and there's a line for the released waste, whether conditional or unconditional. So all the technology components are not very complicated. The only really difficult part is the sorting itself, which was organized by the supplier by a very not complicated, but a very smart arrangement of detectors and fallback possibilities in case that the detection is not really clear. Because everything is already automatized, I think there's further potential using of artificial intelligence, deep learning, and increased autonomy, which will for sure reduce the halts during the process. So what is, I think, shown, you can improve safety, effectiveness, and efficiency, and this is what has driven really that technology. I'll come to next group of short presentation. We had a severe accident in Chernobyl. Everyone on the nuclear world knows that was an unprecedented large-scale accident with loss of barriers and loss of control on the nuclear inventory with large-scale territory contamination. I'm not going to the immediate accident liquidation, but on the long-term remediation, which is now much more triggered by the safety, including the safe waste management, whereas the immediate accident liquidation was mainly on radiation protection, immediate waste diversion options, and to restart the remaining units. I'm not going too much in these projects which are related to the damaged unit or destroyed unit, but I wanted just to show the decision tree which has been developed in the 90s in a joint international team where also PNNL was part of. It's really a risk-based approach. You identify the short-term risks, you identify the priorities, you will take the decision to fund these priorities and you will implement them. And you will look on the long-term risks, which are always related to the inventory. Again, in that case, it was also thought about whether can we convert that site into a disposal site or to a kind of an entombment, which was considered in the former Soviet Union. The expert teams came to the solution that this is not possible. Then you will have only the decision about time. And then, of course, a quicker and a longer term way. In both cases, you want to respect or you will follow the imperative of safety. This decision tree is practically always or almost always applicable in slightly modified forms. In the midst of the last decade, there was an initiative by Ukraine with support of international stakeholders to look on the so-called radioactive waste temporary storage places which have been accumulated during accident contamination. We knew that about 800 burials in 9 of these radioactive waste temporary storage places were given, but unfortunately only two-thirds of the burials were known and characterized, whereas 1/3 of burials were not localized and not characterized. I would just like to highlight all what is what is also known as the red forest. These are the areas with quite high contamination, and I will come to one example of these red forest RWTSPs. In 1998 and in the 1989, there was a survey organized by the Soviet system based on helicopter surveys, and a higher resolution drone mapping have been performed in 2016. I'm not really going on the drone spectrometry. This is not, I think, quite common already, but also the use of LIDAR combined with the other parts. We have tried to find out whether with pure gamma spectrometry you can find unknown burials, and we have re-investigated an area which was already investigated in detail, so we knew where the burials were, and very simply saying that's about 90% or up to 90% of burials can be found by gamma spectrometry, airborne gamma spectrometry with drones, but about 10% or even a little bit more could not be found. And if this comes, you try to do the same in vegetated areas, the detection rate for burials is lowered to 50% or less. And so it is not really effective to find the unknown burials. Which could come to the conclusion that gamma spectrometry is only useful if you have non-vegetated areas and high inventory, which are high radioactive enough. It was thought whether these investigation methods can be improved. Beside the radioactivity, of course, a burial can be shown in the settlements, but it also is showing changed vegetations. So the idea was, can we go and analyze the vegetation by unmanned drones? So normally, if you evaluate all echoes of a LIDAR, you will find a 3-dimensional point cloud. You can try to identify the different trees. So it means segmented. You see here an area. This is the triangle, the area 2.1, I think, of the red forest. And you see that already colored each tree in another part. But more on that, by deep learning, you can really teach a system to identify which type of vegetation it is. And then you can go in the next step and check, okay, if I understand the the trees, then maybe I can, from the vegetation, find possible patterns which will show me trends, and you will come up with so-called probability maps where you will have a trench due to the combined evaluation, which is much more, which will provide more trenches or burials than just if you try to go with a digital terrain model with settlements, because you have the tree distribution, the vegetation composition you will find also. Once you have done, you can of course go for the safety analysis. I will not go too much on detail whether it is worthwhile to remediate all these trenches or only few of them. And it is just the difference whether from what point the safety, you will have a gain in safety by maintaining these RWTSP, or against the remediation, which will be also another exposure. And you see here, in fact, if you go in 200 years or 300 years, it means more or less at least the minimum institutional control area. There's only a very few trenches which are worthwhile to be remediated. So also here you really see that you can reduce the dose uptake for search and characterization of unknown burials. You can reduce the time of characterization of large areas, because a drone is much quicker than people you will send in. And you will have good mapping without or with a minimized dose uptake. And you will have a robust database for safety assessment and remedial action configuration. I'll come to another legacy type of facilities, which are old storages with a standard design as has been used in the former Soviet Union or the Comecon countries, and you will find in many, many different countries, also outside the former Soviet Union. These are legacy sites with uncertainties, again, on the site conditions, the facility conditions, the inventory, and some have very high concentration of volatile radionuclides, mainly tritium. For example, in Kiev, there are so-called storages which have where so-called tritium targets have been put. And unfortunately, on top on that, they have been intruded by rainwater, which are still inside. Part of them could be found out. And the idea was really, is it possible to excavate them and transfer the wastes into nowadays not compatible to disposal facilities which are licensed and compatible to nowadays part. This is just a look on the how these disposal facilities are looking at that. You see you have the full zoo of radionuclides which are possible. Here in bold are only marked those which were very relevant for the safety of the work. And just have an idea, we are really speaking on several hundreds of millions of becquerels per liter of tritium content, which is enormous and which represent an enormous challenge for the safety of workers. The classical configuration element is to take advantage of remote technology, that you don't need to send too many people too often inside, but still, of course, a substantial part of work is to be done by human intervention. The main elements are the standard. It is, of course, a selective recovery. The only thing which is coming is it has been configured as so-called scouting or remote in situ investigation following with the excavation, that you can take a really on-time decision how you will proceed for the excavation and handling of the next part of the waste. The main problem was the discussion about the safety of workers. Although the workers should, the presence of workers, human intervention should be minimized. The initial proposal of the operator was to have the standard confinement on that, and people will be sent with full protection inside, which is of course feasible and which is quite a standard. After evaluation, we have said, or we came out that you can change the system if you go for venting system, and you have on one side the fresh air coming in, and on the other side you will pump out or exhaust the air contaminated. You will protect not only the humans but also the equipment. This is the so-called remote equipment, just a sketch. All these works can really done under much safer conditions. Of course, you can put the people in full protection, but even if the full protection would fail, they would in fact always be in a fresh air stream. This is in fact a technology which is very known from the mining area and which has been adapted for such case. Again, here I think the safety improvement is considerable, and with the safety, also the effectiveness and the efficiency of the whole framework is done. The short summary is in fact what I see is really that if you have the key performance indicators set along safety, effectiveness, and efficiency, then there will be always a demand-oriented innovation which are looking for these three performance indicators. And what I've seen is really that in site remediation in general, but also in radioactive sites, there is continuously improvement to do it better, mostly driven by safety, but also driven by efficiency. Effectiveness is just a prerequisite, but efficiency means always also cost. And I'm not only sure, but I'm sure to predict that this will just continue because innovation will be required. This is in rapid telegram style what I wanted just to present for site remediation. Just an information that these results which I've presented were always joint efforts for a group of experts and companies and organizations. And some of these projects were funded by the European Union, some by the G7. I think people knows very well about it. Thank you very much.
Thank you, Norbert.
Thank you, Norbert. Oops.
Go ahead, Horst.
Yeah, thank you, Norbert. I really appreciate your insights in your presentation. If you allow me a comment, I really appreciate when you mentioned about the controls in terms of avoiding access of people to contaminated sites, because sometimes we, specifically in the IAEA, we deal with member states without ready resources to make higher interventions in contaminated sites, and breaking the pathway of people and the source can be interim solution while the resources are not made available, and we do not need people to not need to be scared that there are simple solutions that can be put in place and that not essentially very expensive ones. So I appreciate that. And a question to you is that when you show in your slide 7 the decision process, you spoke about safe, effective, and efficient solutions, and then in one of the triangles you say safety, effectiveness, and efficiency. And can I challenge you to see that the geometric form can be enhanced to include some other dimensions? For example, sustainability is one of them, because this is essentially the conference we will be holding in November, and also the topic for RemPlex, where we will try to articulate sustainability in the scope of remediation. And I can even add another dimension, is the circularity of bringing the site back to use. So would you welcome those thoughts in these geometric form and essentially consider enhancing that, or do you think that
yes, of course,
the traditional scheme?
I think there were even some IAEA organized workshop where I have deployed that further. But yes, sustainability is something very important, and this is part of all three. But effectiveness, you want to have a sustainable solution. It means it has not just be for the next 10 years, but not for the next 100, but if possible forever, whatever means, but for a very, very long time. Authorities who are representing the safety should and are normally also insisting to show that there is sustainability. And efficiency, I think Bruce made it very clear. There are some elements in efficiency like footprint and things like that. Efficiency is always a contributor to sustainability. That is, of course, what I have seen. Of course, these simplified triangles may mislead to say, okay, I will only look on that. Behind of each point, there are, of course, some more detailed part, but sustainability is for sure something very important. And it is also in the interest on the key stakeholders, although, as I've said, this is a trilateral conflict. What trilateral conflict diagram means always, you can always satisfy 2 at 100% and the third will always be unhappy. So that is the reason that you will have to find a compromise. That is what the main message of these triangles are given.
So I was also going.
Question.
Oh, sorry.
No,
or do you have another question?
Yeah, I don't see questions in the chat, so I will take. Oh, there is one from Jorge. Can you go? Can you get that?
Yes, but before I take Jorge's question, I think I wanted to also comment on this slide, but on the right-hand triangle and adding a third dimension, which is, of course, the general public. And that gets to the sustainability aspects that Horst is raising. So I very much appreciate this slide because it triggered a lot of thoughts in my own head about the complexity, really, of these decision processes. Not just the triangular relationship, which you say, Norbert, nothing can be satisfied 100%, but then adding another dimension to make this more of a pyramid and bring in other conflicting drivers.
Yeah. But I have seen projects failing because people were not understanding that they were standing in the middle of a trilateral conflict. So everyone tries to push his own thing, and then it will not be very sustainable, the results, to take costs. Terminology. Yeah, but that's true, So.
Okay, so should we go to the question we have from Jorge? Are adits and trenches with engineering barriers allowed in the United States to temporarily store soil and rubble contaminated with uranium and cesium-137 tailings? So I'm not sure this is a question, Norbert, you can directly answer because it's asking about the situation in the US. I don't know if you have any comments on that, Norbert, maybe beyond the US experience, or Bruce, if you have any comments.
No, I would like to ask my US colleague to make a final point on that, but my experience is if you come from country to country, even under the same so-called overall framework, like the European Union or IAEA countries, we have some generic common principles and even common normative context, but even then in each country situation may change. The main problem or the main differentiator between the different countries is from what time you will have waste. So it means if you are allowed for putting something on your site for a few weeks without creating a waste storage, which needs a new license for itself, this is a different. But in some countries, you have to already to apply for a license, like for a waste storage, that you can store radioactive material on a site. And then you are, of course, in an extreme complicated logic, and just this license can eat you several years of time, and it doesn't make sense. So the question is really, what are the main needs? That is the reason here, and what are the real requirements? And this is something sometimes which needs discussion. You would, in many countries, we always use the term transfer storage. It is just to say it is not an interim storage, it is just for transfer. We have to put it, we have to sort it there, and then it has to go to the next step. But yes, for the United States, I just would like to ask a US colleague to comment on that.
So Bruce, there you are. Thank you.
Yeah, so I think Dr. Molitor hit it on the head, which is in the context of the question, temporary storage of uranium and cesium-137 in rubble. So we would expect that would not be technologically enhanced radioactivity, but you could probably do that as a temporary measure. But again, it really depends on that regulatory framework that you're working within. If you're working under a Department of Energy owned site, it's one thing. If you're working under a state issued license, it may be a different program. But I think what I keyed into on the question is the word temporary, although I have seen both cesium-137 and uranium identified as naturally occurring or radioactive fallout, in which case those two other scenarios allow for different regulatory processes and licensure for temporary storage configurations. So hopefully that wasn't too vague of an answer, but that's the best I have. Maybe someone at PNNL might have another idea, but thank you for your time.
Thank you. I think I want to ask, and Bruce, you can stay with us because I'm going to pose a question now that I think both you and Norbert might be able to talk to. And it's really getting to questions about how flexible is the regulatory environment in terms of accepting new and innovative technologies, and what type of barrier this presents, and how we can overcome any of those barriers. I don't know if either of you want to comment.
Start off, Norbert, if you don't mind, and then I'll turn it to you. And I think my answer, Karen, would be that there's not a lot of flexibility, but the flexibility is exercised a lot of times at a pretty low level in the regulatory review process. The challenge that I've seen with radiological sites administered by the Department of Energy is the time frame that's required to gain that approval, where the process may be valid, the data may be in place, but the time that it requires to get full consensus from all the stakeholders and a final acceptance of the end state can be quite extraordinary. On the other hand, I think that when I work in the chemical space on innovation, again, it really hinges on gaining the acceptance of the lead regulatory personnel to say, this electrokinetic process for treating this clay zone that might leach chlorinated solvents for 300 or 400 years needs to be evaluated with this new technology, and we have the ability to potentially reduce that time frame to several years from several hundred. And so by building that consensus process, you're able to advance the technology, and really that leads to the commercialization part. So there isn't as much in the chemical and metal space today with scripted programs that might have been there in the 90s that would achieve acceptance. So we really have to do it on a case-by-case basis, unfortunately, Karen.
Norbert, anything you want to add?
I think case by case is for sure the right point. And the question is what you want to do. But I have to, in comparison to the classical environmental remediation, it means chemical contaminated site, in the nuclear sector or in the radiation protection sector, we have fortunately one important tool which goes also under the big umbrella of safety. It is what does mean safety, protection of the general public, of the workers, and maybe also the environment. And this gives you clear indication whether there is a need to do, and then we have to discuss along which requirements you can do that. And if the main stakeholder, the key stakeholder, understands that if something shall happen, I shall not be too rigid. Sometimes it needs to be understood, and we have an imperative. We want to achieve safety because safety is not achieved yet. And that's from their point, you have a very strong imperative. In the classical environmental part, we are discussing about how clean is clean and things like that, and everyone wants to have it even cleaner, and that often blocks a lot of decisions. But in the radiation protection world, I have always seen that part. To make it very simple, for example, a case like Chernobyl, it is common understanding that plutonium has always to occur confined if you go to IAEA rules and so on. But if you insist on that, you cannot handle a site like Chernobyl where you have several tons of plutonium dispersed in the environment, because it is just non-normative. And people have to understand, and I think regulators understand from a very from a specific point quite clearly, that we are out of normative conditions and we want to restore normative conditions. And under this imperative under this logic, You can become more flexible, but it's difficult. There are people who are always shy to take responsibility because it's a matter of responsibility. And that is, again, I've used the term justified approach. It means you have to make it transparent and you explain why you have done it. And it can be even in a conflict with a specific rule which has been defined for the normal case, which is not applicable in another case. You will just, either you want to do it, you want to improve the situation, or you just say, okay, we will discuss about that 20 years and nothing will happen. That can also be then the case. Yeah.
Horst, I see you've raised your hand.
Yeah, I have a comment and a question to Norbert. In your slide 8, when you talk about example of waste minimization, you mentioned that ex situ confinement and excavation and disposal, it has a high acceptance. I would kind of ponder here that it might be high acceptance for the community from where the waste will come out, but it may be very contentious for the community where the waste will go to. So maybe you want to comment on that.
Yeah, it's a good point, because this has been maybe a little bit too sketchy, but if you have licensed disposal for radioactive waste or for other waste,
in this case,
then this problem does not exist. The problem is for you, if you are the implementer, the owner, or whoever of a site, you have to find that disposal who is willing to accept it. But if you have it, that is okay. There's another part, or an exceptional part, which I've also seen. You create a kind of a disposal. It's not a disposal, it's an on-site confinement of a compartment of wastes you have excavated, maybe also conditioned. But this is, of course, much more delicate. But even for the unrainers, it means the people neighborhood, it is, of course, the decision whether you will accept an improved situation or you prefer the original situation, because the waste cannot go anywhere else. So that is the part. And this is different from country to country. And it's a term which I haven't displayed here. It will come to the so-called socio-economic context. Yeah, you have countries, you have enough space and nobody is living there, but you have to pay attention, because nobody doesn't never exist. There are also and people you just forget to look at. Yeah, and you have really to make the socio-economic analysis in some cases, and we had to perform that, yeah, to show that this is the only way. But then you have really to look who are living there, what are the traditions there, will you change the tradition, the cultural heritage, and things like that is all part of this discussion.
Yeah, and my question is regarding your slide 17. I was thinking while you were making the presentation, the methodology of 3D vegetation mapping. So you're correlating the colors in your aerogram with the transfer of radionuclides from the trenches to the trees. So in which time frame after the burial that would be, this correlation could be possible? Because thinking about an accident, if it was immediately after the accident, that kind of 3D mapping would suggest deposition instead of uptake. So let's imagine that these has been washed. Just a minute. It is
what is shown on slide
out.
17. You can do it online during the survey. It means practically.
But how long after the material has been buried? Do you have any guess to that?
How long? Well, here in that case, the material has been already buried 30 years. Yeah, so it means you have already quite a intensive succession of plants. Yeah, so that's not even the first, but already the second and the third generation of plants already partially. But you can do that immediately afterwards. Yeah, so that is not a problem. So the problem is there are a lot of plants which will just come up within the first year. Yeah, after an accident. And it would be good to have even, or for example, we had a discussion, unfortunately, we didn't manage that. If you have total burn down, like we had in the Red Forest 2 or 3 years ago, unfortunately, we had the pandemic. We said this is an ideal way to observe the whole new succession after burning down of a contaminated area to see how vegetation will develop. So you will have a dynamic development. This is just a snapshot. This is 30 years afterwards. We look at the trees and we look, or we try to see whether, of course, we know the trees, that's one part, but the idea was really to see whether the vegetation pattern will show a trend on which they are growing, yeah, because the trees, the idea was the vegetation will change with what is on their roots, you know? And there is, of course, on one hand, the vegetation will behave due to the contamination differently, and the other part is because the soil is different, because you have a burial which has a total different biosynesis and accessibility to plants, which will change the pattern of plants. You know, that is the two things. But the main part is, this is deep learning, deep learning algorithm. We are even not asking what a forest expert, although forest experts have worked in that project, will expect, but we will just see whether there will be patterns to be found. So these are just the technologies as we have used in Industry 4.0 for other parts, which we have just used now for investigation.
Thank you, Norbert. Yeah, I'm sorry, we have 2 minutes left, and I know people are starting to disconnect. And Chris, I believe, signaled you wanted to make a comment in response to the observation from Mohammed.
So Mohammed commented when you brought up the stakeholders that don't forget indigenous groups, and I would second that. That's an issue for Canada. Certainly in the United States, we have tribal nations that we deal with all the time, particularly in our legacy management sites. So yeah, there's a variety of folks that need to be involved as you implement technologies and look at end states for a site.
Thank you. Thank you for underscoring that. Didn't want it to go unsaid. And I want to share the final comment, maybe, is an observation from Claudia, our participant, who said that it's not regulatory barriers aren't the only thing. It's really finding companies, contractors, service providers who have the relevant experience and capability to implement these new technologies. So that's another aspect that presents a potential barrier. I think and Chris provided a comment to that. I think we're right at the end of our session, and I want to thank Bruce and Norbert again very much for your presentations and all the work you put into preparing for this and supporting our two networks. Yes, applause. And I want to thank everyone for their time in attending and in joining us. Kelly has put a reminder linking to the RemPlex Summit in November, where we will be covering many of these same topics in various case study sessions or in technical sessions that have been organized. So if you go to that link that Kelly's provided, you can see our initial program is posted. Horst, I will turn it over to you if you'd like to make any closing remarks.
Yeah, thank you, Karen. Thank you to the folks in PNNL for working together with Environet. Thank you, Norbert and Bruce, for the very nice presentations. And just on the side of the IAEA, I just want to mention the projects that we are running. They are very related to this issue. I just mentioned a publication that is almost ready to be released that deal with the remediation of legacy trenches. I put that in the comment. And regarding stakeholder related issues, we have the Maestri project, which deals with decision-making, participatory decision-making, take into consideration the social dimension. So we are mostly welcome to be part of this project. And if you want more information on Environet, the best way to do is to type Environet IAEA in your browser, and you get there and you see more insights on what we are doing. Specifically, I want to highlight this partnership with PNNL. That is, I believe, a very strong contribution we are providing to the member states, highlighting that Karen Smith is the chair of Environet. So thank you all for the participation. We have a good turnout, and I'm looking for the next seminar, next webinar. And I guess we get a hint that acid drainage may be a very interesting topic for us to explore. Thank you.
Yeah. All right. Thank you, everyone. Goodbye.
Thank you. Bye-bye.